See if we can see it on there. Oh, you know what? Let me do this because I think I have it up. So, oh, damn it, I don't have it. Let's see if I can pull it here. Oh, there. Okay. So this is the schedule as it's written. So we're supposed to be talking about like barometric law, hydrostatic equilibrium, energy transport, but I think it's all going to move. So I do want to talk about icy bodies that we talked, I think 4-1, I think that was the final score. And so we're going to get into stuff like tides and resonances. And that's orbital dynamics. So necessarily we're going to talk gravity. We're going to talk optics. So it'll feel a little out of left field, but it's kind of necessary to understand how these icy moons have a source of energy when they're so far from the sun and there's no radioactivity, right? Okay. So what that means is I'm going to try my best to move this all down and sort of bring up perturbations and resonance and a little bit of like 2 and 3 body problem. We'll probably want to go into rings right away just because that's going to have so much to do with the dynamics that if you just wait another 5 weeks before you see rings, I think you'll have forgotten it all. We'll just see it and then apply it. And then we'll go back to this when we start talking about atmospheres. And of course, we're going to revisit Mercury and Earth tides as well. But we'll see that later. Okay, where is my cursor? Let's fucking go. Okay. Come on. Yes. Okay. Not a disaster. How's everyone doing? Thanks for not my dogs. Busy. Yeah, good. Okay. My legs hurt. I went to San Francisco. I went to a festival and I danced and I didn't eat enough. My body's in pain. Yeah, we're totally in. So yeah, it is what it is. We're surviving. So today I really want to talk about the structure and the composition. I'm going to start with the Jovian satellites. Jovian satellites are just too good an example of a lot of the features that we're going to see in the outer solar system. And when you talk about anything like you talk about Io, you need to discuss tides. You talk about local evolution, and in particular in the Galilean satellite system, which is just the 4 inner moons of Jupiter, you're going to necessarily need to talk about perturbations and resonance because those objects are in resonance. And that will come up again when we talk about rings. You'll see that the ring structure of Saturn is deeply dependent on resonances therein, right? Okay. So we'll talk about long-lived tidal heating, what that looks like, volcanoes on Io that have been erupting for billions of years, and how liquid water can be present on a place like Europa, where you should expect from the size and the radioactive heating contribution that it should be zilch, that it should be frozen all the way through. And of course, you can go ahead and make those comparisons to the other outer moons in the Galilean moon system, because where you don't have that tidal heating, where you don't have eccentricity, you don't have volcanoes. You don't have a subsurface ocean, right? That makes sense? Okay. Wow, but it really didn't come out good. Why is this not? Probably looks better on my screen, but this is not that clear in here. All right, whatever. These are 2 volcanoes on Io, and they are erupting. in symmetry. So Io is the most active body in the solar system per capita. And we have all these beautiful pictures of Io eruptions. You get a sense of the scale here. These are massive plumes of material. And if you recall from 2300 or from ASTR 1000, this material that's very light makes its way onto Jupiter, and the stuff that's heavy falls back on the surface and colors the surface this yellow and orange color. And what's the yellow and orange color we see here? What? Dirt? False. False, not dirt. Sulfur. See yellow, think sulfur. What is dirt, by the way? Soil and dirt are used exclusively to respond to anything on Earth, because many people will argue that you need microbes for it to be considered dirt. Okay. Otherwise, you're talking about sizes. Sand is not a thing. Sand is a size. Right? Rocks come in many different sizes. Big rocks. Then you have like boulder, right? Like this fantastic American joke where they'll name anything other than the size of a freedom unit, right? Like, oh, a giant rock the size of 2 washing machines, right? So rocks are just size all the way down. And by the time you get to sand, that is of a particular range of sizes. Fine-grained sand, coarse sand, etc. Right? You keep going, you still have the same mineral. Right? As long as you make that mineral, right, that still counts as the mineral. And so if you can keep grinding it up, you can get powder, which is just fine sand of a certain type of mineral. Right? Is that fair? Okay. All right, here's our bodies. Here's the Galilean satellites. And I put the moon for size comparison. Right? So if Io was in our night sky, and then one wouldn't be active. But if we were at Jupiter at the same distance, they're the same size. It's pretty remarkable, doesn't it? Europa is a bit smaller. Ganymede is significantly larger. And Callisto is the second largest of the 4 of the Galilean satellites. We call them Jupiter's regular Galilean satellites. There's a significant number of regular satellites. We'll talk about regular versus irregular satellites a little bit later. But there's reason to believe that these 4 formed as Jupiter was formed. Very similarly to how the terrestrial planets formed around the sun. Almost analogous. Okay. These things are not going to mean very much unless you've memorized distances, right? These are the same major axes in centimeters. But I do want you to have a look at these numbers here. This is the orbital eccentricity. You'll notice of these 4, there are non-zero eccentricities. Which one has the largest? Let's see. Everyone agree? Europa's is about 1%. Is that discernible from a picture? Remember we did that example. Maybe I didn't. Where it's like the Earth is also 1%, and then a perfect circle, and they look at it. Let's look at the revolution period here. Excuse me, what does that mean, sidereal revolution period? Excuse me? Oh, that's the unit. What does it mean, the sidereal revolution period?
The the same face is in the direction of like the planet. I guess to better explain it, like with Earth, like when there's one full rotation of it, it's the exact same face that appears on the sun in contrast with the planet.
Yeah, so you're hitting on a very important word there. And the word that I want you to notice was the use of the word rotation. So the word rotation and the word revolution mean two different things. So sidereal is showing the same face, that's 100% correct. This is the sidereal revolution. That means it goes around something else. Rotation means it goes around its own axis. Does that make sense? So what's the sidereal rotation mean? Yeah. And what's the sidereal revolution? So if we measured the year for someone who was born and raised on Io, the year for them is 1.76. Okay. So it's whipping around Jupiter, going around Jupiter fast. Good. What's this next one? 3.55, Ganymede 7.5, Callisto 16 and change. Okay. That's the sizes, that's the masses. Here's the albedo that kind of tracks. This one here, very reflective. That orange do be reflecting good. Europa, like kind of whitish in a lot of places. Europa, Ganymede, still quite light, but Callisto looks weird and dirty. Okay, that's certainly this one. Let's look at these MR squared values. What does the number in front of the MR squared mean? The uniform object is 0.4. Okay. So how centrally concentrated is the material? And the dumbest thing that we could make got us up to 66%, which is where all of the material was an exterior shell, non-physical, doesn't make any sense, and nothing was on the interior. So we could somehow create that fake structure. You can get up to 0.66. Uniform was 0.4. You did other examples, I hope, in the homework. And here's some values. So who's the most differentiated? Yeah. Okay. Who's the least differentiated? Is that weird? Did you expect that? I did not expect that.
Because it's the active volcanism. If it's there's volcanism that got to liquor on the interior, which means there has to be some differentiation.
Okay, okay. But are they differentiated? They're all definitely differentiated, right? Yeah. There's something weird about ion. We'll get back to that. Look at these densities. What's ion made of?
Sulfur.
Well, sulfur's definitely on its surface. So it must have sulfur somewhere in its body. You're absolutely right. But what's the density that it's made of?
Oh, rock.
Rock. That's weird. Right? What's Europa made of? Rockish. But these other two are ricey rock. Icy rock, right? Okay. Okay. So imagine we start with something Ganymede sized, right? Icy rock. And you slowly begin to lose all the ice. Then you can conceptualize of something that's more similar to Io's density, right? Because we have no expectation that there should only be rock at Jupiter's distance. The only reason Jupiter exists is the availability of ice. The availability of ice tells us about the core, right? That we can build a planet as big as Jupiter. So there must have been stuff to build icy satellites. Okay? The fact that it says high density is telling us about its evolution. Focus on a couple more things here. you can't exactly just see that and memorize that, but that is a 1, 2, 4 resonance. So take this number and divide it by this. Take this number, 7.15, and divide by that, 1.76. Someone else do Europa, 135, divided by 17. Okay. How close? 4.065. It's pretty good, right? Pretty good for Europe.
2.017.
2.01. This is pretty dang good. So the resonance here between Io and Europa is within 1%. And the resonance between Io and Ganymede is probably less than 6%. We didn't use all the digits, right? Okay, these are strong, low order orbital resonances. Now let's break what that means. Okay. Low order means the numbers, the n associated with the orbits. So a 15 to 17 orbital resonance is not as necessarily important as a 1-2. Okay, 1-2s tend to happen more frequently, and so they can contribute more energy long term. Okay. These are icy. All their surfaces are icy, except Callisto looks weird. We'll talk about that. And 2 of them have very strongly rocky interiors from the outlets. But we might assume, since they're all differentiated, that they all probably have a rocky core. We'll have to find out if that's true. Okay. So here's the picture. So we think that they're all differentiated, but Callisto does not have an iron core. Ganymede has its own magnetic field and has a liquid. This is Io here. Europa. Ganymede. The Callisto is undifferentiated. Kind of. It's got some differentiation. This is Io. No liquid of any kind. All the liquids. Europa has a thick shell. Ganymede has a giant amount of liquid underneath the surface. Now, whether it's probably not in liquid form, but stuff that could contribute to icing. So then this is an icy crust on undifferentiated rock. Right. This trend of average density that decreases from Jupiter is going to match the mass fraction. And what I mean by that is, grab my pencil. Okay. Just to have folks recall. I got my legs. Okay. Yeah. Okay. So when we look at any disk, this is going to be orbital distance from the central object. Okay, and this is going to be what we use as sigma to be the mass. Or usually unit area, we would use volume, whatever you want. That's some mass. Okay. So the mass density for protoplanetary disk, for the one that all of the planets form out of, is something like this. This is before you do any sort of chemistry. This is just when you start with gas. Okay. So this stuff, up to a certain amount, contributes directly to the object forming, like the sun. Okay. And then you have all this stuff in here that starts to get heated, right? And you start losing a significant fraction of ice. Right? So you might end up with a mass fraction that really ends up looking more like that. Okay, and then Jupiter forms there, right? So when we think about them in terms of the composition, you have this trend of decreasing outward density, but now you need to think of it not in terms of the original protoplanetary disk, but in what's the availability, because close to Jupiter, you don't have a problem of a really bright sun. You have a Jupiter, and Jupiter has its own issues with its disk, but it's not blowing away the ices. And so you could form objects of much more ice. Okay. So you'll have some different trends like this, and then maybe you'll have a different slope for ices. Right? This might be the rocky slope, and this might be the icy slope, and just seeing how they're mixed. And what you expect to have happen is the highest density stuff will be in the middle because it has access to the highest amount of rocks. And then the densities should decrease as you go out until they flatline and everything is made of ice. Does that make sense? Most of the mass is formed of in silicates when you build the planet, and that's what the interior of Ganymede shows us. Sorry, let's show. That's fine. Okay, good. All right. Oh, this is working. Yes. Well, imagine that this is showing us flying low over again. I'll find the visual. So we've talked. Hopefully, you know this already. Europa is completely covered in Mars. Surfaces are actually not that heavily cratered, and you'll see this when you look at Ganymede and Callisto. Even though they don't have as much resurfacing, they don't look as ancient as them. Okay, the moon has been absolutely bombarded. To really think about where this stuff comes from, most of the bombarding of the moon comes from the asteroid belt, nearest neighbors. Being behind the asteroid belt, when Jupiter pushes you, and let's say you're the asteroid belt here, if I push you and I send you into the inner solar system, you're more likely to hit something in there than you are to come back and hit the thing that perturbed you. So to some level, that's not that unexpected, that the Galileans should be less. But for Europa and Io, there's almost no craters at all, right? So this means that they are like extremely young surfaces. And when we see Enceladus, especially in the Tiger Stripe region, you'll see no craters there. And that indicates like essentially brand new material. Right? If you have no asteroid belt, if you have no atmosphere and you have a surface without a single discernible crater, that's as new as possible. Right? Because you still expect really small stuff, like we see meteors every night. You still expect a tiny thing to create a hole. Okay. Let's have a look at this fun video for Juno. This is Jupiter. Oh, let's turn this off again. Please play. Everyone practice together, create this I've seen it in present in my mind. Right? Yeah. Surfacing events, not necessarily only That's like it's what you need. Okay. Outside, move the close approaches. Not just, I mean, you take images like this. I'm taking a picture. Let's say I have an object that's red. Okay, this is how much light I get. Okay, and this is color. So this is purple, blue, green, red. Oops, two words. Five. What does the red mean? Think if I'm drawing a spectrum of a body. One side is one. Right. The higher over here, right? Points over here. Here. It's a lot of green. The red thing. Going up.
Well, it's more than that.
If it's green. If it's a red thing. Wait a minute. I expect these dots to go down. If it's red, do I have a lot of blue? Okay. Okay. So now let's take a photo. A photo takes an RGB image. RGB. If you send down a bunch of pixels that have captured zero blue light, you're wasting information. So if you just say, well, all right, I know I'm not getting that. Let's take an IRG image and just scoot it to the right for the units. Okay? So this one becomes that one, this one becomes that one, this one becomes that one. Now, I'm not sure that's exactly what they did. They can make lots of choices here. But in all of spacecraft photography, because cameras are not limited like our eyes are, we can take information that has way more than 3 channels. We can take 15 different channels on the spacecraft and then pick and choose what we want to present. So in some cases, blue might mean something, right? That might be the ozone filter and only showing places where ozone is. That might be an infrared image, right? That only shows you where the heat is coming out of the surface. Okay, sorry, distracted you with cool pictures. That's IO. Sick. That's a volcano, the surface. The SO2 frost, which is the sulfur dioxide frost, is the color that you see here. The structures that we see all over that are rainbow, none of these are impacted. Not a single one. They're all over. But that Europa, folks who don't remember, Europa is got thick water, subsurface water, ocean. And I say ocean very loosely here. Ocean really should refer to water on top of the crust. It's kind of an inappropriate, way of saying subsurface ocean. Right? Maybe we should call it that mantle. We call ice rocks. Now I'm just being completely inconsistent with my terminology here, but this is kind of what we do in the field, call this subsurface ocean. Really should be the mantle. It's nice. Europa's surface looks like an oceanic ice pack. So Jupiter having a huge magnetic field means that when we look at Europa, we fly by it, we can look for deviations in the magnetic field. Okay. So ice is an electroinsulator. You're out and it's a lightning storm. And for some reason you're in an icy area. Apparently running on the ice is a better idea than running into the water. Now, you play a risky game there, because if the ice breaks and you fall in the water, then you die from freezing and from getting struck by lightning. But rocks and ice are pretty good electrical insulators. And so they are not responding very quickly to the magnetic field of Jupiter. But an icy, salty, a wet ocean brine that might exist in the subsurface, in fact, we know that it exists, will respond quite well as an electrical vector. So most moons sort of plow through the magnetic field and then they really don't interact with it. There's wrong. That's definitely not the case for Europa, and I can kind of show you these ideas here. But for example, you have something that's an insulator, you may be familiar with this if you're taking ENM2. Yep, okay. So insulators, magnetic field goes right through. No problem. ENM fields, waves just going right through. If you're insulating, if you're conducting though, you don't want to go through the surface because that will create bound surface currents and surface charges that will work to immediately negate the effect of the magnetic field that is already present. So magnetic fields, I would say, are like rubber bands. They want to return to their original state. And similarly, if you have a material in here that is unmagnetized to start with, it doesn't want to gain magnetism. So this liquid in here moves through, and all of the electrons and molecules in there reorganize themselves such to make sure that it maintains no magnetic field on the material, because it never started. Okay. So it has to have the right conductivity to repel the field. We can see these deviations. If I fly over the surface here, you can see the magnetic field change, like normal, 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 normal. And here I see all bunched up, and then it bunches up, unbunches again. And that signal can only be explained by the presence of a subsurface conductor. And because we can fly over it in many different directions, you can see if there's any preferential direction, and there is. We think, yeah, so let me just finish this. Those two other ones, Ganymede and Callisto, probably also have subsurface oceans. We saw that in that picture of Ganymede, so it's very substantial. The question there is how much of it is liquid, right? So for example, Ganymede has a very large, let's call it a mantle, an icy, right? Because it kind of is agnostic as to phase. You could have a section at the very top that is liquid, and the rest be ice underneath it, or vice versa. You might have an electrically conductive icy brine, maybe lower, where you have high enough pressures that it will melt again, and the top might be frozen all the way, like a large lithosphere. Okay. One thing to keep in mind, I don't know if I talk about this now or later. Yeah. So for Europa, one thing that I want to mention here is that the ice shell is probably something like 15 kilometers thick at a minimum. The farthest you've ever dug on Earth is about 12 kilometers. We did that in something like 25, 27 years. So we are not going to be able to drill into Europa, drill baby drill, and go look for space fields. Here's gotta update this as well. It's probably more. It's 22 years old. That's maybe older than some of you. So the irregular satellites of Jupiter, there tend to be highly inclined orbits. So what that means is that the regular satellites, they're all in the plane with the rest of Jupiter's rotation. So Jupiter is rotating like this, and perpendicular to the axis of rotation is a plane that the four Galilean would lie in. This here is Callisto. This is Themisto, innermost irregular prograde satellite. Prograde means going in the same direction as Jupiter's rotation. Retrograde means going in the opposite direction. Okay. There are 5 irregulars. Let's see, 1, 2, 3, 4, 5. Yeah. I have to turn off the lights. This is good. Right? There was 11 retrogrades discovered in 2001. They're out here, really far out, and there's 14 other previously retrogrades. There's something like 67 satellites. So when we get into formation, of course, we want to understand how that happens. People know how that happens. How do you get a moon? What? You make it or you capture it, right? Those are the ways that we think that we understand how moons get. How many moons does Earth have? Wrong.
No, man.
Yes.
Oh,
Oh, okay. No, not the space station. Moon, by definition, cannot be man-made. That's a satellite. All right. The answer to the atmosphere burns up.
No. Yeah.
Yeah. So we have a moon, a baby moon, called a moonlet. It will be friends with us, I think, November 26th. Then it'll leave. Why? How?
I was out of curiosity, is it possible to see with one of the meats?
Probably not. It's real small. You might be able to get it, if we can track it with the EV scope. But then you can do time on it. It's real small. It's a great idea, and we absolutely should try it. But let's not get it. Okay, so how do you get a moon?
that, it enters, so. Earth has a magnetic field, right, and the one that's pulled in by its parent. keeps it in. So if it enters that orbit that we have, and it has enough energy, it's kind of like a loop. So it stays in the orbit.
Okay,
It's gonna fly by.
yeah, so you're 90% there. You're using the idea of the flyby, which is right. But you have one more thing to consider. So you know that it's leaving. And you're thinking that it's coming in, right? And then it's going in. That seems reasonable. That would be a flyby. But what happens is, just like you're talking about here, it's doing the gravity of both of these objects. And we can get it to slow down. And if it slows down, it'll go into orbit around us. So what happens is if I'm a rock and I do this, it doesn't count. And that happens all the time. We have stuff that happens. But if I'm a rock and I do this, that counts. So because we are interacting not just with the Earth system, but the moon is going to change the energy enough so that it stays in orbit of both of us. Right? This is obviously the big attractor. The Earth is the big attractor. But the Earth-Moon system permits something not to just fly by, because in a flyby, we either go on one side or the opposite in order to either gain or subtract speed. Right? So if you can get it just right, and this does happen, if we want to go around Jupiter, for example, here's Jupiter. You want to fly on the side that's right close to Jupiter so that it takes energy from you, so that you can just do a tiny little burn right here and go into orbit. Right? Whereas if you want to use Jupiter to get away, you go on the other side, so that when you burn on this side, you get a huge boost coming up. That's how flybys work, right? But here we have to take advantage of the fact that there's two body interactions. So even as I slow down, now I'm getting slow enough to be felt by Earth, right? And now I'm in this bigger system. So he's going to do a bunch of weird loopy loops, and then he's going to get flung out again. Yeah.
Could we send out a spacecraft?
And this is a diagram. That's not real.
Could we send out a spacecraft to help capture it, like just keep it? Would that still be considered a moon, or would that be considered a satellite?
At that point, if you change the orbit,
Yes.
it becomes a satellite. If you let it live its thing, it's a natural. But natural moons are very hard to come by. Why does Jupiter have some? And the hint is not this. They're big, but so it's basically it's big. It's got a big gravitational interaction, right? Basically, it's this giant disk that it can interact with. But you tend to need a third body. Okay, and you need to have a third body because you have conservation laws that you're required to maintain. So what do I mean by that? If I have angular momentum, if I have energy, and I convert between potential energy, which means being bound, and kinetic energy, unbound, I need to be able to conserve those quantities. What's the simplest way to conserve those quantities when you're trying to become captured? Give the energy to something else. Okay, so let's say Jack and Jill go down the hill. Okay, here's Jupiter. Here's Jack. Here's Jill. I know it's super helpful, right? Okay, so Jack and Jill are going along their merry way. They are binary asteroids. They are asteroids that are orbiting each other, and they're best friends. They've grown up since kindergarten. They've gotten through a few fights. They've smashed into each other. They've broken off some pieces. They're just living their life. Okay? They fall down this gravity well. Okay? And they're falling in a way that is going to bring them really, really close. Okay? And they get separated right here. Now they're feeling the gravitational attraction of Jupiter a lot more. And they're speeding up tremendously. And one of them gets flung out. And the other goes in. Okay. This is called the capture hypothesis. Right? This is the way that you do this on a computer. Because Jupiter does not have a sizable moon that can just randomly grab stuff. You don't have hundreds of satellites, you have one maybe for a month. But if you want a stable satellite, this is how you have to do it. Okay. But if this happens, then we should see that irregular satellites don't care about the formation of the original moons. Because if an asteroid comes in like this, there should be no preference to prograde versus retrograde. There should be no preference to up versus down, right? They should just come in, get captured, one gets flung away, and one gets sent on its, Make sense? Okay, they look like asteroids. That's what they look like. On the left is Metis, Atastrea, Almathea, and Phoebe. Like these. So moon exerts, Jupiter's very moon exerts a large tidal force on its moon. This is going to, this is going to tell us about the interior of these moons. The orientation is changing continuously. Usually because the moon is rotating at a different speed that's going around. So that means that the tidal force strength is changing continuously in eccentric orbits, even if they're just 1% eccentric. And because we're typically talking about bodies that are differentiated, you're going to have ices on their surface. And ices, of course, are the most deformable because it takes the least amount of energy to heat them, right? At least in these systems. So you're going to rapidly stretch and relax them for the course of the orbit. How long was Io's orbit? Day and a half. So one full rotation, which includes getting closer and farther, right? Every day you're changing the surface of Io. You're wondering why it's so messed up. Okay. So whence comes the heat? From where? Remember, we have to talk about conservation laws. So there's an exchange of energy, right? In order to heat up that surface, you have to take it from somewhere. What is losing energy? What? Jupiter. Jupiter is losing. Oh, great. It's just.
It's pulling. It's. It's losing. I'm trying.
That's good. No, it's great. You're doing it faster than physicists. Conservation laws, physicists. What? Where does the energy come from? Okay. Only place to get it. Right? You know the moon is moving away from us. You know why? Because what?
Tides.
What tides?
Earth tides.
Earth tides. So the fact that the Earth has liquid on its surface, the high tide and the low tide, every day, 2 times a day, results in the moon moving away from us. Make sense? Okay. So energy is lost due to heat and radiation, and that changes the orbit of the moon. Okay. This first slows down its rotation, so you can lose rotational orbital energy first. Let's say you're spinning, right? You create tides on your body, and once those tides align and you lose the rotation until you're synchronous, then the only way to lose energy is to lose orbital energy. It's to move away from the body. Okay. You need to talk about torque in order to change angular velocities. Remember that, of course, momentum and angular momentum are conserved. So where do the torques come from? Okay, I'll say this more slowly. Let's say I have a rotating body. I want to change the rotation. Applying a force on it will change the linear acceleration, right? I want to change the angular acceleration. So I need to create a torque. Just slow this down so that I'm always seeing the same part of the expo marker when I look at it, right? Where does the torque?
How do you want to say it's tides of
Tides of it's definitely the tides. Okay, so let's remember what torques are. Here's linear momentum. E equals mv. What does mass mean? How hard it is to move something. Good. What's force? So when we think about force, it's the rate of change in momentum per unit time. So typically we say MA, but that is incorrect because M can change. This assumes a constant M. This is the way you should think about force. the PDT. Momentum is the important concept, especially when you have a loss process. Angular momentum is the torque, or sorry, is the lever arm crossed with the momentum itself. So this is an inherent quality that is described with respect to a rotational axis. So what I mean by that is I have, let's say, an object that's moving. I would say that angular momentum would be with respect to the center of this object, and then this would be the distance, right? But its angular momentum, of course, would be quite different if I put the center of the system over there. Even if it's doing the same motion, because from the perspective of this object, by defining an R, you inherently are defining where it's rotating with respect to. Okay. A different way of thinking about this is there's an analogy, of course, that the moment of inertia, the resistance to rotation, and then the angular rotation around some rotational axis. Right? Okay. So this whole idea of angular momentum is not quite the same as the linear momentum, but they are analogous. Right? This one is frame dependent, and this one is an independent, until you get to special relativity. This is an independent quality, right? Okay. But torque, which is R cross F, is dl dt, and we saw before dp dt, which is the rate of change of the momentum. This is the rate of change of the angular momentum. How much am I rotating this object? Okay. And similarly, it's just I times the angular acceleration. Okay, so we can think about torques like forces in a rotating sense, right? Okay. N is the torque. I don't use T for reasons that perplex me. It's R cross, so it's going to be out of the way. So if, for example, I want to close this door. Okay. Where's R? Which way?
Out.
Out towards here, right?
Yes.
Okay, this is R. I want to close the door. Which way is F? Yeah, this way. Okay, I'm going to put my hand on this part of the door. I'm going to press it. And now which way will it rotate? Ah, good. So do that with your left. Yeah, do that with your, sorry, do it with your right hand. So now do, yeah, good. So right, R. So R cross F. Rotates in, right? You see how it gives you the direction? Cool. Cross products to work. Good. So let's do some more math. Oh, this is fun pictures class. So tidal bulges, right? There are these deformations that can exist. They can exist in rocky bodies as well, and you can certainly see them when you see the interior density of these giant moons. Even in our moon ourselves, right? We know that our moon has a bulge that's closer to the Earth, right? So these tidal bulges, the results of fluid, partial fluid interactions with gravity, because they can have differential pulling, and that differential pulling basically will freeze in at some point and you'll literally have a frozen body that resembles this interaction. We have bulges that can lead or lag the rotation of the moon. So to define some of these terms, here's the parent body. Think about Earth here, probably the easiest thing to do. This will be the moon or a satellite, some type. This is the planet rotating. This is a prograde satellite revolution. Okay, we'll see how the torque changes for retrograde satellite rotation. And greatly exaggerated bodies, greatly exaggerated distances, and bulges. Bulges are tiny, pretty small. In order to draw this, you'll have to Go. Okay. Let's calculate the torques. So let's see if you can draw all this together. Here's the body. Here's the satellite, call it moon or whatever you want to call it. We're going to place the center of the rotation of the object. Let's say this is us, the Earth. And we'll call this long one arm. Now let's say you have a bulge. Okay. And this bulge is at some arbitrary angle. Okay. That arbitrary angle theta. Okay. So now we need to define a couple of distances here. And this will be the distance to the near bulge and the distance far bulge. How do you find it? That would be great if we had any. But we don't. So if we look here, okay, what I have is this is the distance r out to some distance. This is say the top of the rotational bulge, and then this is the distance r n, and this is the distance r. Oh, yeah, probably, yeah. But this, we have a law for this.
Boston.
Well, cosine. Right? Very similarly with the one on the bottom. Let's redraw that so that it makes more sense. Okay. What's that? Yeah, no, that's right. Just so you can see it all the same way. But this is now. Stop. What do you say? Oh, so law of cosine is good. We don't need the law of sine. Law of sine is actually fine. This is fine. You remember where to find this? No? Okay. You can find it in the vector geometry class, but exactly how we just said, there's relationships here between these different distances. You know how big this is, r minus x. And then you can create an equation for that. And you can create an equation for how long this is, and then you can relate it to this one. Notice that this part here, Rn squared equals, what is cosine theta when theta is pi over 2? Can you say that again? No, what is cosine theta when theta is pi over 2? 0, right? So if this is the case, right? And this is pi over 2. And this is r. And this is R, and this is Rn. Shouldn't we get Pythagoras' theorem back? And do we? Oh. Okay. It's annoying geometry, but it's still beautiful. Okay, sorry, it's too much. All right, there's R. Good, you got it. So that's how we set up geometry. So that's the R that we need for our angular momentum, sorry, for our torque. So now we can make some fun approximations. Let's remember, of course, that the orbital bulges, the orbital radius R tends to be much larger than the planetary radius. This is almost always true, except for maybe a little bit like Cuba. But what you can do is you can say, so leading orders here in 1 plus a big R, this is the planetary radius divided by the little r. Okay, this is going to be essentially equal to a power series. And you can kind of adapt the power here for the work that we're going to use. So what I mean by this is if you have something, we're going to see why this is true. If you haven't seen it, we're getting methods. We're going to see how we can use this to take a leading term. So here you have 1, that's going to be the most dominant number here, plus something smaller than 1, plus something smaller than 1 squared. And something smaller than 1 squared is certainly much smaller. And therefore, basically, just this term is what just this 2 terms is what matters, right? Everything of order R over R, big R over little r, quantity squared, and larger, useless. So if you have a power series, which is of the order n, you can just take this. Agree? No one has a problem. Good. So the torques, only the torques on the bulges matter. Okay. So there's mirror symmetry for the rest of the planet. And the only thing we have to care about is this region. Make sense why that would be? Yeah. Because everything that's being pulled over here is being pulled over here. It's only here that I'm not balancing and pull over here. It's the mirror symmetry that matters. Come on now. There we go. Okay, we can do it. Don't freak out. So let's look at the nearest bulge. That's here. Okay. And I want to find out how much force. I can use F equals and then G and M over R, right? Sorry, R squared. The delta M here is the weight of the bulge. How much material is in my bulge? The little m is the Southern. The Rn I got from the law of cosine. Okay? And I rearrange. Or I don't, no, I didn't rearrange because I called it R. Good, I didn't rearrange. So that's just there. Okay. Now we need to write some modifications. So I can pull out an R squared from each of these terms, right? If I divide this term by R squared, I get 1. Good. I can divide this term by R squared, and I get R over R squared. Good. I can divide this by R squared. 2 over R. Okay. Well, so now I have something like 1 minus 2 over R plus 1 over R squared. And didn't I just say before what you should do there? What? Let's go back. Go back, okay. If you see something of this form, what do you do? You only take the term that goes up to r over r and you drop anything of higher order. R over r squared doesn't exist. So let's look at what I said here. Okay, you pull the r squared out. Now I have something that's 1 minus 1 over r plus 1 over r squared. What did I listen to myself?
You should get rid of it.
Yeah, you just throw that away, throw it right in the garbage. Useless. Okay? And this is approximately equal.
So would two cosine data represent n in the previous equation that you provided?
N or A?
Oh, excuse me, A.
Good. Okay, yeah, you can do it for the other side. Data time, not data. Where does the tidal bulge force maximum? For what angle is the tidal bulge force maximum? That's right. Maximize this function, find out where the tidal bulge has the largest power. Okay, I'm running out of time here. We can. Yeah, let's wait. Maybe. We can talk about torque on the parent button. But this is basically gonna give us the understanding of how we can calculate tidal bulges. And in particular, if I give you something like how much a parent body has rotated. For example, I grab an object like the sun, or sorry, an object like the moon. And I tell you that it was once rotating at this rate, and now is rotating at once per 28 days. I will ask you to calculate how much or how rapidly did it slow down. And you'll be able to do that because you have the beginning rotation and the end rotation, right? And you have the reason for this rotation. What's the final state of the Earth Moon system? Put it in. One face of the moon is one facing one.
It's facing one facing the other. They're going on right same way.
They're very close, very close. That's exactly what we expect to happen if the sun wasn't involved. So as the moon recedes, it'll eventually recede far enough that it won't want to be friendly. So we will lose our moon because it's literally moving away from us because of the tidal bulge. So we have enough angular rotation that the fact that the orbit is changing is going to win out. But eventually, if you didn't have that system, if you started very close, you would expect them both to be facing each other. The moon's obviously already in tidal. Good. Well, all right, we'll investigate that a little bit more in your homework.